Hello everyone. So in the previous video that I had posted for today, we talked about some applications of surface integrals and we gave somewhat detailed actual calculations of the results, specifically how to find surface area using a surface integral and how to calculate heat flow through a surface using a surface integral. In this video, I just want to do a quick overview of additional applications of surface integrals. This video, though, I will not be going into detail on any specific calculations of physical quantities. I'm just going to overview what kind of quantities could be calculated using surface integrals. So once again, we can find mass from density using an integral. And we've seen that, depending on what kind of object you're dealing with, different kinds of integrals are used to calculate the masses of different kinds of objects, right? Like if you had a one-dimensional straight object, which had a linear density function that was just a single input, because this object, being a straight one-dimensional object, could just be represented using a single position input, x. Then the mass of the object was found using a single integral from whatever is your initial x value to whatever is your final x value of this one input density function. So single integral for a one-dimensional straight object. If you were dealing with a two-dimensional flat object, then the density function was going to be a two-input function. The mass of such an object was calculated using a double integral of that density function over the region in two-dimensional space that the object occupies. If you have a three-dimensional solid object, then your density function would have three inputs. And in this case, we saw that the mass was calculated using a triple integral of that 3D density function over the three-dimensional region that the object occupies. Now, what if you had a thin object like a wire or a rope, but it was bent or twisted so that it was no longer straight, so that instead it formed a curve through two or three-dimensional space? A 1D object that's not straight. In this case, the density function would still be a function of two or three variables. Because this object occupying 2 or 3D space, different positions would have to be identified using 2 or 3 coordinates. So our density function has multiple inputs, but in some sense, our actual object is only one-dimensional. And in this case, we can find the mass using a line integral. The line integral of the density function over that curve occupied by your object. Now, finally, what if you're dealing with a two-dimensional object that is not flat? A two-dimensional object that has been bent or warped or twisted so that it does not lie flat, but it occupies three-dimensional space. This is the situation where you would calculate the mass using a surface integral. If you're dealing with a two-dimensional object that's not flat, then your density function would have three inputs. It would be a scalar field with three inputs because locations on your object would have to be identified using three coordinates. But even though the density function has three inputs, the object itself is not a solid three-dimensional object, which means that a triple integral is not appropriate. Instead, we would calculate a surface integral of the density function. We would use a surface integral to calculate masses for objects that are 2D but are not flat. So each of the 5 different kinds of integrals that we've learned about in calculus so far can be used to calculate masses of differently shaped objects. Flux integrals can be used to measure heat flux through a surface, and likewise they can be used to measure things like electric flux, magnetic flux, if you're taking, for example, like physics 3. In addition to that, if you're dealing with a surface S that represents, for example, a filter, and you have some fluid with a constant density, let me just call it rho. So, for example, maybe you're dealing with flowing water, which has a density of around rho equals 1 gram per centimeter cubed. And you have some vector field, let me call it V, that represents the velocity of the various fluid particles in this moving water, this moving air, this moving whatever you're dealing with. If you take the surface integral of the density times the velocity, this can be used to calculate the rate at which mass of fluid is passing through your surface or your filter. So the velocity is capturing literally how fast the fluid is moving. The density is what is getting you the amount of mass of the fluid that's passing through the surface. This surface integral captures at what rate does the mass of this fluid flow through this surface, this filter. That can be calculated using this surface integral of this velocity vector field times density. One of the nice physical formulas that I like to show students, both in this class and as they progress into differential equations, is the equation that you see on the fluid dynamics page of Wikipedia. Namely, this one right here, mass continuity, the conservation of mass equation in fluid dynamics. I love showing this equation to students at the end of Calculus 4 because it contains so many of the ideas that we have studied throughout this entire class. Have a look at this, folks. So in this equation, we have a certain volume, a certain three-dimensional space, which is being called V. And then we have sort of the exterior of that three-dimensional region, the shell on the outside of that region, and that is what is called here S. We have some fluid that is moving around in this three-dimensional space with a density here called rho. That's the density of the fluid. We have the vector field u, which is representing the velocity of that fluid, and t is representing time. Now, on the left-hand side of this equation, the first thing that we see is a triple integral over this volume of the fluid's density. A triple integral of density over this volume. So let's copy this down and let's see if we can interpret what that piece of this equation means, physically represents, based on what we know so far about triple integrals and densities. So to mark this up, remember we just said earlier that when you integrate the density function, when you do a three-dimensional integral of a three-dimensional density function, that's getting you the mass of some solid 3D region. And so in this context, this triple integral of the fluid's density over V is going to tell you the total mass of fluid inside the 3D space called V. Now, working outward on this left-hand side of the conservation of mass equation, we see this total mass, and then we see this partial derivative applied to this total mass. The partial derivative of the total mass with respect to time, with respect to t. And remember that derivatives tell you rates of change, right? In particular, this partial derivative is talking to us about how the total mass inside this three-dimensional space is changing over time. So this is what is being expressed on the left side of the equation. This partial derivative of this triple integral of density is saying, okay, how is the mass in this three-dimensional volume called V changing over time? Now let's cut over to the right-hand side of this same equation. Here we see the notation that's used to represent surface integrals. In particular, we have a surface integral of density, rho, times the velocity of the fluid. So this is exactly what we just wrote down earlier in this lesson, the surface integral of fluid density times velocity. We remember that what this means is the rate at which the mass of fluid is passing through the surface. So by setting these two quantities sort of equal to each other, what is being asserted in this mathematical equation is the following. The only way for mass in a volume to change is for mass to pass through the surface of that volume. In other words, when you're dealing with an enclosed space, mass cannot simply, appear and disappear at random within that enclosed space. If you are gaining mass into the space, it is because mass is being pumped into the space. It's flowing into the space somehow, and it has to flow into the space through the boundary, through the border, through the surface of that space. Likewise, if you're losing mass, that is because mass is exiting the space. The mass is not just spontaneously disappearing, and it must have exited the region by passing through the surface and going outside the surface. And so mathematically, what this is doing is capturing what we call conservation of mass. Mass cannot just spontaneously appear. Mass cannot spontaneously disappear. If mass increases or decreases, it's because it has flowed into or out of your system somehow. So that is the conservation of mass equation in mathematical symbols. Now, many students are curious what is going on here with this negative sign in the equation. And that just comes from the fact that if you remember from our lesson on orientation of surfaces, we noted that by default, when you're dealing with an enclosed surface, the default orientation is outward. So by default, when you calculate a surface integral, outward flow through the region is considered positive. However, outward flow would cause the mass inside the region to decrease, which would make this derivative negative because derivatives are negative when the quantity is decreasing. So in order to make the signs match up, where the surface integral outputs positive values when you flow out through the surface, but this partial derivative is negative when you lose mass through the surface, that's what this negative sign is here to do, to make the two signs match up with one another. Just as one final remark, I won't go into too much detail about this one because many of you may not have studied anything of electromagnetism at this point, and I'm definitely not an expert on electromagnetism either. But if you have a look at some of the electromagnetism laws and rules and formulas, you will see a lot of the ideas and formulas and notations that we have learned in this class, right? So here, for example, is a triple integral on the right-hand side. Here, for example, is a surface integral on the left-hand side of Gauss's law. Here as well, we have another surface integral. Here we are relating a line integral to a derivative of a surface integral and Faraday's law of induction, and so on and so forth. Here is another line integral. Here is another surface integral, and so on and so forth. So if you end up studying any electromagnetism, surface integrals, line integrals, double integrals, and triple integrals are all used very heavily in that context as well.